Okay. Let's think about this. First of all, as we start, one thing I wanted to point to people's attention is, again, in the grand scheme of what I was hoping to accomplish in this class, somehow we want to talk a little bit about what contracts are and what, how options are priced, and that was sort of the first part. The second part, we're talking about time series analysis, because everybody thinks stock data is interesting. Well, one way to get stock data is that you guys here are actually fairly lucky in that because you have a good business school here. The business school has access to various financial resources, and one of which, for example, at my home university, we do not have, as just an example. One of them is the Reuters, I think it's called X3000 system, and it's this, supposed to be basically an online, provide all the information or a lot of the information that an online trading terminal would have. And part of it is things like historical data about stock prices and things like that. Now, I'm expecting that we're going to get a student lecture here in the talk here in the next week or two about a different financial database called CRISP, which is interesting. But the library is having a series of presentations about how to use the Reuters system. And so if you're actually interested in this kind of a game, if you're interested in getting access to financial data and and viewing it and correlating it and doing all kinds of things with it, I would recommend that you go and sign up for some of these these lectures, the training classes for this. I put the information about it on the front page of the course website, so you can go there if you want to find out more about that. Any questions about it? Again, having access to these things, if you're interested in playing with financial data, is a very, very good thing. When my students have had to do course projects back at Stony Brook, they were reduced to doing things like scraping Yahoo Finance to get their time series data. Okay, and it's much better if you actually have it coming from a real database source, which is curated and where there's where there's a lot where there's a lot of data there. Any questions? Okay, the second question is that we have our the second announcement is that we have the homework is due today. Okay, now that was defined. I noticed. Did everybody get the? No, I guess today is defined as being till midnight. Is that correct? According to the email I got from the submission program. How many people have submitted their thing already? Okay, how many people have not submitted their thing already? Okay, majority. From the people who submitted things, how good or bad were your predictions? Did you feel that the options price programs did something, or is it that they were completely hopeless? How good or bad was it? Did you come away convinced that the theory had power, or did you come away convinced that you didn't know how to do it?
Somewhat accurate, but not always.
Not perfect, but what would you say if you had to give a percentage error or something like that? What do you say?
10%, whatever.
Within 10%. Okay, so now that's an interesting amount. That suggests some level, a good level of predictive power, right? What about you? You also submitted yours, right?
Yes. I think they more or less the same comparing to the real prices.
Right. Okay. So, any questions from anybody about the assignment now? Okay, or about how you about what is expected, or or any of the technical issues involved with that. Okay. Again, a 10% error is not. First of all, notice it's not clear what an error means. Okay. There is a price that something is trading for, and it's trading at it because people are what do you call it? That's what people are buying and selling the securities at. That's the current price, and that's set by supply and demand. On the other hand, what we would expect is that these pricings are governed largely by the theory, and that's really what you guys are basically saying. Okay? Any questions? Okay? So I look forward to seeing those assignments. Okay. Any other questions about anything going on in the world before we go on? Okay. Last class. We started talking about correlations and autocorrelation. I want to go through this a little bit more. Okay, I want to continue. Last class I jumped around a couple of places. I'd like to go through this a little more smoothly this time, because correlation analysis and autocorrelation analysis is really sort of the underpinning to how you do time series analysis in the real world. And what we talked about here, just to remind ourselves, here is a example of an autocorrelation function for car sales data. And what did that mean? The x-axis was the lag, okay? How many days, again, a correlation was, remember, a statistic computed on two time series of the same length, measuring how well they went up and down in sequence. A lag L correlation would correlate a sequence with a shift of it by L days. Okay? So this is going to correlate a lag 1 correlation. We'll show you how much today's value correlates with yesterday's value. A lag 2 shift says how much does today's value correlate with the value from 2 days ago. Okay? And in general, this in fact I guess is representing years, in this case not days. The time scale here is years. This was car sales data. And what this sort of showed us was that the number of cars sold, okay, in 1 year correlated extremely well with the number sold the previous year, less well than 2 years before. And in general, you would expect that these autocorrelations would decrease with time, okay? With the exception of different kinds of phenomena. Like here we saw there was a bump up after 7 or 8 years, okay? And the argument there was that cars wore out. People bought new cars every 7 or 8 years. And so there is somehow a correlation between sales there. Okay? Any questions about it? Okay, so the other figure here, which we'll talk about a little bit more, is what these bars are here showing. These blue line, those bars there, are showing some sort of an error bar as to how big is it that the correlation, the autocorrelation, is significant. Okay? So if you think about it now, if you take two random sequences, let's say you take 50 points, two random sequences of 50 points, if you correlate them, you're going to get a correlation coefficient. We would expect it to be 0, because they're independently drawn random numbers. We would expect no signal. On the other hand, because it's a random thing, we would not, although the mean is 0, it's 0 in expectation, in reality we would expect some fluctuation of what the correlation of two random sequences is, right? Because these are numbers drawn, okay? You would expect there to be a significance, okay? There would be some, I mean, if you know, I'm saying this very badly, but it's sort of an obvious thing. Okay, if I give you a bunch of random numbers, okay, and here I have A, B, C, and I correlate them. If these were drawn independently at random, and these were drawn independently at random, the expected value of the correlation of this is 0. But the odds that it's 0 is very small. It's like if you flipped 100 coins. The expected number difference between heads and tails is 0, but almost certainly you will see some difference between heads and tails that is bigger than 0. Okay? The probability of getting an exact 0 is small, even though the expectation is 0. So you would expect that there's going to be, if you correlated these random sequences, you would not see 0, 0, 0. You would see small number, small number, small negative number, small number. These bars here represent, actually I think it's the line 1 over square root n. Okay? Where n is the number of points in the sample. Okay? And it gives us an idea here of only when the autocorrelation, when the correlation gets above these lines, is it probably significant. Okay? Any questions? So if we looked at this thing, there is some predictive power in knowing how many car sales, okay, happened 12 years ago to predicting the number of car sales today. But it looks like it's diminishing to the point where that fluctuation by the year 13, 14, okay, is probably going to be statistically irrelevant. Okay? And that's sort of what these error bars are doing. Any questions? Okay. So, when we talked about, let's say, random numbers, if we were correlating random numbers, the sort of professional word for random numbers, okay, in this business is called white noise. White noise is what you somehow get when you turn on a radio when you hear static, okay, when there's sort of just random noise here. We would expect that for a series that is random, like stock returns, okay, if you took the correlation function, okay, the autocorrelation of stock returns, you would expect that you would see after one day, today's return has very little to no correlation with yesterday's. And you'll see no correlations anywhere on there, or very, very small ones. Okay? We say that its time series is white noise, okay, if it consists of independently distributed, okay, uncorrelated observations with constant variance. Okay? And so we would expect that that stock returns, by this definition, would be white noise. Okay? The autocorrelation of such a series is going to be, we expect it to be 0 for all legs, okay, except for 1 when it's perfectly correlated. It's a leg of 0 when it's perfectly correlated. Any questions? When people talk about Gaussian white noise, they mean it properly where not only is the series uncorrelated over all legs, okay, but that the values that you get are normally distributed, okay. So in this case, it would be more, centered around around 0. Any questions? So one of the big jobs in time series analysis is telling whether or not your time series is in fact white noise. Okay? So if you think about it, I've been sort of saying that return sequence, okay, is white noise, okay, is unpredictable, is random. There are a lot of people who don't believe that, okay? They sort of believe that they can predict what tomorrow's returns might be on a stock, or something like this. Okay? The question of whether in fact stock prices are really noise, the returns in stock, the returns from stocks are noise, okay, is a hard question. Okay? But it is clear that that's kind of the question that we're really going to be interested in here. Okay? And in particular, we're going to be interested in taking a time series data and constructing some kind of a model for it. Okay? Some kind of a model that will have some predictive power for what the next value in this time series is going to be. Okay? We define the residual, okay, given a model and a series. Okay? We would define the residual as being the difference between our prediction, okay, and our, let's say we have model observations R and a model F. The difference between our model and our predictions is what we mean by the residual terms, okay? And if we have a very good model of predicting a time series, we would expect that our residuals are going to have the property that there is no correlation in any of the residual terms. Okay? There's somehow no signal left in our errors. Okay? If let's say that I had a prediction, I am telling you, here's a function that you're trying to predict. Okay? And here is my, I'm going to say prediction. Okay? And when I subtracted this thing, the difference between my prediction, these are the observations, these are my predictions. If the difference between my observations and my predictions looked something like this, my model couldn't be very good. There is clearly something not captured in the model yet. If the error terms have a linear structure to it, right? What we would really like to have, even if they were not linear, if the error terms looked like this when I plotted it, there would be something in my model that my model hasn't quite captured, right? There's some seasonality here. And this would show up as an autocorrelation that's non-trivial with this period. So what our goal here is, when we're trying to model something, what we're going to be interested in doing is, our modeling is only sort of going to be complete when we look at the residuals, the errors that we're making, and see if we can prove that it is somehow indistinguishable, or as indistinguishable as possible, from white noise. Any questions? Okay? Again, if it was white noise, the properties of it would be that the autocorrelation would have an expectation of 0, and the variance is small. Okay? And this gets back to the argument that we had here, that the reason why we had error bars, okay, is that whenever there was an autocorrelation that went above this error value, the square root of that, the variance was higher than we expected. That would mean that maybe there is something still in our signal that we haven't picked up on. Any questions? So let's think a little bit more about autocorrelations of real functions. Okay, how many people here are familiar with Walmart? Okay, some people. Is there a comparable thing to Walmart here? Walmart is the big store, the biggest store around. What biggest series here? Let's say Park and Shop, for all I know. Okay, if you took a look at the daily sales of Park and Shop, what would we expect that would be like? Okay, I tried to find some daily sales data on the net, and I couldn't do that. Okay, but take a look. I think we can probably predict what's going to sort of happen. Okay, that first of all, there's going to be a certain amount of noise. Okay, in the daily sales, because at Park and Shop, if it's a rainy day, the sales go down. Okay, and you know, on a sunny day, it goes up. Right? We would expect that there's a certain average level of sales, because people probably need, or a certain, it doesn't ever drop to 0, presumably. Okay? We would also expect that there are some periodicities in this data. What, if we were to take a look at Park and Shop sales, do we think that if we took a look at the autocorrelation function, okay, of Park and Shop sales, do we think that their sales today are going to correlate well with the sales yesterday? Okay? I would expect that that's true, right? Or the Park and Shop sells $1 million worth of groceries a day on average, right? There's some up and down fluctuations. But we would expect that there is probably a correlation with today's sales. If we look at it 2 days from now, the sales 2 days ago, do we expect that the correlation is weaker or stronger than 1 day? Probably a little bit weaker, okay? Because somehow if it's raining 1 day, the rains probably tend to last, I don't know, rains may very well last for more than 1 day, okay? Do we expect that the correlation of sales for Park and Shop, the autocorrelation function, is always going to go down with the number of days? When would we expect to have a bump up in the autocorrelation function? one thing we would expect is that every week there is going to be a bump up. Why is that? When you're doing the autocorrelation, you shift over a week. You're comparing Sunday sales with Sunday sales. And probably Sunday sales are higher than Monday sales because everybody's free to go shopping. Does that make sense? So if we look at what we're probably seeing, if we look at the autocorrelation function, we would probably expect it to look something like this. Where every 7 days, every multiple of 7 days, there is going to be an increase in the autocorrelation. If you look at it 2 weeks from now, is the correlation 2 weeks from now going to be higher than the one 13 days from now? I would certainly expect that. Okay? Any questions? Are there any other seasonal things with Park and Shop? Okay, or any other periodicities here that we might expect to see in sales data? Okay, or is it all captured by weekly things? Okay. I would guess that for a lot of businesses, you end up having yearly spikes. Okay, I know Park and Shop is a good example because people go to groceries. But are there annual effects in how much people buy? Okay, in America, around Christmas time, people buy a lot of everything. Okay, and so you would expect that the sales, if it's a Christmas day, are going to be, or a day before Christmas, are going to be extremely high. You would expect that if you carry this thing out further, by the time you get to about 365 days from now, you probably get a relative bump again. There's seasonal effects. Maybe during the summer, people are too busy to shop. Okay? And so, comparing, a July day to a July day, you would get a higher correlation that way. Any questions? The neat thing about the autocorrelation function is that if we look and see where there are these periodicities, this gives us something to tell about how we should be modeling this. Okay? It's clear that if we wanted to model sales data, we need to factor in weekly and possibly annual effects. Any questions?
If anyone tried to do some Fourier transform to analysis of frequency.
So one question here would be, so one way to do this perhaps might be to do Fourier analysis, spectral analysis, which we'll talk about a little bit later on. And that would be sort of representing it as a function of science. But note that, so that's another way to capture some of this idea. Okay? But we're going to look at a class of models today, these autoregressive models, where it is actually very natural to capture seasonal effects. Okay? Any questions? One final thing that comes up in issue that comes up in time series analysis. When you read any book about time series, they talk a lot about whether a time series is stationary. Okay? The mathematical tools for time series analysis that we look at tend to assume something about, about the nature of the time series. Okay? We say that a time series is weakly stationary if the mean of the if the mean of the time series of the value is constant. Okay, the expected value of the time series is constant, and that the covariance, or equivalently the autocorrelation, depends only upon the lag. What does that mean? Okay, it means that if we're analyzing a time series, there's a question of do things change within the time series. If you're trying to figure out the mean of a time series, okay, it is a different problem if for some reason something is going to happen in the middle of the time series that causes the mean values to change, okay, or whether or not you assume that there is somehow a constant set of conditions, okay. If we had a time series where here was the stock market and then the world collapsed, okay, which maybe we're observing now, okay, that somehow there is a change of regime. And it wouldn't make much sense to compute the mean of this kind of a function, or the autocorrelation of this kind of function, because somehow the world has changed. In general, when people talk about time series, they will talk about, say, that the theory of what they're doing holds for weakly stationary series, which means that the mean is assumed to be constant, and that the covariance, okay, depends only upon the lag, meaning that the lag L autocorrelation of the whole function is taken to be, is assumed to be, from the same distribution as the lag L correlation of any subpiece of it. Okay? Any questions about that? So, in general, once you have these kind of series, the kind of tools that we use can be used to analyze it. Any questions? Okay. So, our goal is to take a time series and to construct a model of it so that we can do forecasting. Okay? Certain models, okay, will be defined on the basis of what we know about what's underlying it. When we talked about Walmart, we've defined that their sales data should have certain properties, because we know somehow that we're modeling sales data, and sales data should have these kind of periodicities to it. We know that if we were building a model, it would be silly not to capture what we know about the world outlying it. If we have a model of, let's say, what stock prices do, okay, it would be silly not to use our model, okay, if we really understand and believe our model, to help to identify what the forecast is. So if we assume that stock prices really are a random walk, okay, and there's unbiased and stuff like an unbiased random walk, if we want to forecast what tomorrow's prices are, if this is really the principle by which the prices work, our best guess for tomorrow is that tomorrow's prices will be the same as today. Sometimes we can build models from the first principles that we have. The other class of models that we can build, okay, come from fitting data, okay? And these are sort of the ones that we're probably going to focus on here, okay? Any questions? So, when we talk about time series, when you read, let's say, a book on time series analysis, again, we are picturing people in here are computer scientists. There is a different way that statisticians think about time series than computer scientists do, okay? This is my belief from interactions with statisticians, okay? Statisticians are very interested in the limits of what can be rigorously inferred from data, okay? That if you go to a statistician and you give them a data set, they will ask questions. Is it stationary? Okay, are things unchanging? Is it? And they will be very interested in what can be rigorously inferred from the data and what you can derive confidence intervals and stuff on. If you go to computer scientists and say, build a model to predict stock prices, the answer is typically going to be sure. Okay? And they will build something that will take a model, okay, and build a, put it through some kind of a black box, okay, to come up with some kind of a pattern recognition approach or something like that that gives an answer. And whether the answer is justified or not is not something people care about as much, okay? My plan for the next couple of lectures as we talk about time series modeling is to first talk about how statisticians would, in general, model time series before we go through some of the pattern recognition procedures that are more common in computer science. Any questions? So, when people look at modeling, there is a sort of three phases of building any kind of a model. Okay? There is the model specification phase, which is where we think about what our model should probably be, what mathematical properties or what formal properties our model should have. Okay? again, with the Walmart example, we would expect that if we were building a model for Walmart data, there would have to be something that captures periodicities, that captures seasonal effects, okay? Or else it's a bad model. There is a model fitting phase where once you have selected a class of models that you think fit your time series data, you actually have to set the parameters for it, okay? And you know, again, and that can be done by software, it can be done by numerical methods, something like that. And then finally, there is some kind of an evaluation process where if you want to build a model for your time series, okay, you then have to, once you have your model, you need to somehow go back to your original data and come up with some kind of a model analysis as to whether or not the model is, is effective. And this might involve looking at things like the autocorrelation function of the residuals. Okay, is that, are there still artifacts in that we might be seeing? Any questions? When we look at modeling, one of the goals here, there's often lots of different models you can use for any particular time series data. One of the big goals that we want is a model with relatively few parameters in it. Okay? A parameter is somehow the coefficient that we might compute or solve for in our numerical procedure. In general, a model with a smaller number of parameters is better than a model with a large number of parameters, even if the fit is not so good. If you wanted a model to perfectly fit Walmart data, okay, one way to do it if you have n points of sales data would be to compute an nth degree polynomial that exactly passed through any one of the points that you had. The good news of that model is that in fact it would perfectly predict, that the residual error between the prediction and the observed value will be 0 at every given point. The downside is that the model is not going to be very robust. Okay, that typically a much better model would be one that had a very small number of parameters and almost fit our data, would be preferred there. Any questions? And so we're going to look a little bit later at methods that help us judge whether a model is, what the trade-off here should be between the error of our model observes and the number of parameters. Any questions? Okay. One thing as we again move through this last class, we talked a little bit about estimating volatility, and I sort of made a hash of this question of exponentially weighted moving average models. Okay, for predicting volatility. Okay. Any questions? How many people? Do people have any questions about how to predict volatility for this assignment? Kind of made it discussed briefly last time. Were there any questions remaining about how you would predict, measure volatility using this kind of a model?
Can we invent models ourselves?
Can you invent models yourself? As far as I'm concerned, you can do whatever you want on the homework. So if, let's say, for the purpose of the homework is, again, trying to help you predict, what you call it, option prices as best you can, and to see how well your models work. We took a look at one. We could look at the standard deviation of returns. That would be one. Okay. The exponentially weighted moving average model was better because it adjusted to local changes. Okay. And you can decide. If you have another model in mind, you may do so. Any questions? Again, the basic idea of an exponential weighted moving average model, it was sort of a smoothing technique. That's probably the easier way to think about it. Maybe this is what I messed up last time. Is that we said that today's prediction is going to be some multiple of yesterday's prediction plus 1 minus that weight of the yesterday's observation. Okay? So we're going to update our estimate as a function of what we saw, what our estimate was in the past, plus our observations. Okay? And if there is the function we're estimating is fairly stable, then our prediction of the past presumably still is highly correlated with our prediction of today. Okay? And so our prediction for today should be some function of our prediction in the past updated by some amount. Okay? And that's basically the principle behind this. Okay? So in the standard, one of the famous volatility models that is widely used of this type, they said that 94% of the weight, okay, would depend upon our current prediction. Will depend, 94% of it will be based on yesterday's prediction. Okay? With 6% depending upon yesterday's observation. And then the next day as we go through it, if we want to pick a day from now, it's going to depend upon 94% of this value, of which 6% of it was yesterday's observation. You can see how the dependence on our history is going to decrease exponentially. Any questions? So this is a simple, widely used model for volatility prediction, and that's what I encourage you to try. Any questions? Now, one thing that's not so clear, though, okay, is where this 0.94 comes from. Okay? Yes, question.
Is the observed volatility the difference?
I would say that they're trying to predict the standard deviation of the return values. Okay? Presumably, this is going to be what the standard deviation would be of one term. Okay, which is, I think, just that one term. Okay? So if you're trying to predict the percentage deviation of returns, okay, this should be the percentage change yesterday. Okay? Any questions? It's important somehow the units, if you're combining this with this, the units of this have to be the same as somehow the units of that. So once you know what you're trying to predict, okay, the quanta here has got to be in the same, the observation has to be mapped to that same unit. Any questions? So the question that just to think about is, where do you go about getting this 0.94 from? Okay? In this particular model, who decided that 94% of the volatility today is a function of today's volatility is explained by somehow the global history in the past? It would seem that you should be doing it by some kind of a fitting method. Okay? That if you knew somehow, let's say you were trying to fit the best exponentially, best smoothing model for what the volatility would be. Here you've got these daily observations that are coming in, the changes in the stock price, the changes in the returns every day. If you knew what the real volatility was, okay, then somehow what you would like to do to fit that parameter is to find which value of that parameter here, okay, that parameter lambda best predicted the underlying volatility. Now there are a couple of different problems with this if you wanted to try to select that parameter. One is in the case of volatility, what is the real if you're trying to figure out which parameter best fit the volatility. There's some lambda parameter here. Using a different value of lambda will give you a different prediction as to what the volatility is. How would you go about finding what that lambda is? And there are a couple of different complications here which are interesting, okay, for this this particular problem of computing volatility. One is that there is somehow it's not clear what the gold standard really is, okay? That it's not clear that anyone really knows what the real volatility is today. If you're trying to come up with a prediction for a constant that will help you make good predictions for volatility, there needs to somehow be a right answer. If you knew the right answer for the volatility in the past, okay, then in principle you can use some kind of a numerical method for it, okay? But if you think about it, volatility is not the kind of constant that you can measure directly, it seems, okay? So what is the gold standard that you might use? The second problem is, even if you did have a gold standard where you knew what this was, okay, you're now trying to say, what is the constant, okay, such that I can multiply this times 0.94 plus this times that constant, plus this times that constant times 1 minus that constant, plus this times 1 minus that constant squared. What is the value of that will best predict this thing? The standard way of doing that might be something like a least squares fit, and we'll talk more about that later. But the trouble here is that because it's an exponentially weighted thing, the constants that you're multiplying each one of these things depend upon each other. And so numerically, it's not so easy to solve these kinds of things. So this is an example where if let's say you had a gold standard and you wanted to find out which constant worked best, you need some kind of another numerical method that's maybe a search procedure where you try a bunch of different constants, okay? It's not obvious what the right, let's say, that there's a method that will give you sort of the provably best constant here. Any questions? Now, one interesting thing that's going to get us a little away from time series, but it's kind of an interesting thing when we talk about measuring volatility, is that there is somehow sort of a gold standard measure for what the real volatility is at a particular time. Okay? And this is actually captured by something called the volatility index, okay, the VIX, which is actually kind of an interesting statistic these days. Okay? How can we really compute what the volatility of stock prices are? Okay? That, as an abstract thing. The interesting idea here is as follows. We know from our Black-Scholes model that our Black-Scholes model predicts what an options price should be based on everything except on a bunch of factors like the interest rate, like the strike price, like the time till it expires. There were like 6 parameters that went into pricing options, of which all were directly observable, except the volatility price, the volatility value. The reason why you guys weren't aren't having any trouble finding out what the strike price of the option is because it was given. The volatility is something that somehow is not directly observable. But if we believe in the Black-Scholes model, and we believe it does a good job of pricing the options, okay, and all the other constants are known except the volatility, we can in some sense take our Black-Scholes equation and use it to solve for what the volatility is, given all the observed values that went into it and the and the current options price. Okay? And this gives us a way to compute what is called the implied volatility. If we assume the Black-Scholes formula is right, then solving for the volatility gives us somehow the right estimate for what the volatility that day is. So what's interesting is there is now an index that is published, okay, and that actually represents an index that you can actually buy and sell options on, called the VIX, which computes the volatility by taking a bunch of options, okay, maybe all the options that expire 30 days from now, okay, in a particular index, let's say the S&P 500 index, and compute some kind of an average. For each one, you can use this to compute a volatility estimate by averaging those together in an appropriate way, okay? You can now compute a volatility, okay, independent of actually looking at the changes in prices, okay? Does everybody see how this is an alternate way to think about volatility, and maybe one that is better grounded than just averaging over the time series? Any questions?
So, if I understand you correctly, people price options based on what they assume volatility, based on what they assume volatility is going to be based on some observations. And now the VIX index works backwards from what people are pricing options as and builds volatility.
Right. So the assumption is, right, so basically what you're saying is true, but I'd say it a little differently. I would say people are pricing options based on whether they want to buy them or sell them. Okay? They sort of have some general guideline as to what things are worth based on the Black-Scholes formula. Okay?
So then do people applying to option traders, or do people developing, people using Black-Scholes model, do they actually use the VIX index as the volatility?
That would seem like a perfectly good thing to do. Okay?
So you're getting this weird feedback.
So you're getting this weird feedback. Again, the idea here, I think, is as follows. Okay? We have an a priori theory based on the Black-Scholes for what the price of the option should be in terms of some observed volatility some volatility parameter. Okay? Now that Black-Scholes model did make certain assumptions about the world that aren't perfectly true. Things about transaction costs being zero and all kinds of other things. Okay? So we're now going to go and take the prices, okay, that the options are actually trading at, and work backwards to say what is the assumed volatility that the traders must be thinking, okay, in order to go through and do that. Okay? Any questions? Okay? So what's neat about this is this gives us a well-defined index of volatility, a way to compute a volatility, okay, that is orthogonal to averaging all of these the observed differences. And what's more, okay, is it is a well-defined mathematical thing, and so you can build an index on it, okay. And in fact, there is a volatility index here. So what's one thing you can do? You can compute this time series as a function of current option prices, okay? And you can also basically trade on it. So one thing that's interesting is that the Chicago Board of Options Exchange has a contracts where you can actually trade on the value of what the VIX index actually is. So you can buy a contract for 1,000 times the cost of this index. Okay? You can offer, again, just like any other option, there's put and call and put options available for VIX options at many different prices, strike prices, just like with the other options. We interpret a VIX of 15 as implying a 15% annual change. Okay? Where, as we talked about before, we can convert the annual volatility to a monthly volatility by dividing it over the root of the period of time associated with it. So a VIX of 15 implies a 4.3% change over the next 30 days. Meaning that it's computed that there is a 1 standard deviation probability, or 68%, that the absolute value, okay, of the 30-day return will be less than this. Okay? Any questions? So what's interesting about it is that you have this orthogonal way to compute what the volatility is, depending solely upon what options prices are currently traded at. Okay? And this index is well defined enough that you can that you can trade on it. Okay? Any questions? And now, once people can trade on it, that gives another way of looking at it. We talk about feedback loops. Trading, if you buy and sell an option on what you think the volatility change is going to be at a certain time, that gives you another estimate, a way to think about what the volatility changes are. Any questions? So here is a graph of which again you can't see very well, showing you estimates of the showing you the value of this VIX index, okay, as a function of time up until October of this year. So if you look at it, it typically trades in about a range of about 15, okay? Meaning that the expected up and down movement of a stock market, okay, in the course of a month is about 4%, okay? There are periods of time when this volatility increases dramatically, okay? This corresponded to the tech boom and bust, okay? Then things settle down, and this corresponds to today's, okay, period. This, when I made the chart, was the volatility, the value of this VIX index for October of 2008, where we are now, which, as you notice, is higher than any period of time in history before. Okay? In fact, it was now, according, if I'm correct, it was about a week and a half ago that it hit a record of 80. Okay? Any questions? Which sort of means that there is a prediction that there is a high probability that prices would move up or down by something like 20%, okay, over the next month. That's really what an index like this means. Okay? Any questions? So what's interesting about this, if you look at this kind of a series, the thing that's interesting about it is, for one thing, it shows that there's a high degree of correlation, okay? That the value of the VIX index today is quite well correlated with what it was in a few days from now. That's because if you look at it, it doesn't move very fast. Okay? It is subject to sudden shocks where suddenly something's going to happen and it goes up. Okay? And that's the world that we live in. And there's also a vision that in times of calm, it reverts back to a mean level. Okay? And that there's somehow sort of, in principle, some kind of a calm level, okay, of volatility that should eventually ensue. Any question? And one reason why the notion of reverting back to a mean is interesting is, suppose, let's say, you wanted to predict, using one of these exponentially weighted moving average models, or something like that, what the volatility is going to be, okay, a certain number of periods from now. Okay? Let's say here is our window of observed volatilities. Okay, our standard deviations, if you wish, okay, of price movements. The exponentially weighted moving average of these things is going to be higher than the last value that we had, the initial value. And so our prediction for the volatility tomorrow probably would look something like this. What if we now want to make a prediction for the next day? 2 periods from now. This is today. Using the exponentially weighted moving average kind of model, we can come up with a forecast for what the volatility is tomorrow. Does everybody see that? Suppose we want to predict what it's going to be like 2 days from now. The logical way to do it is to simply say, this was our observation. Our prediction was really happened yesterday. Okay? And to count that as the next observation. And now compute the exponentially weighted moving average from here. And that's going to essentially make this value now more important than this one, which would have the effect of making the next prediction higher than it was. What am I trying to say? If we kept plugging in the value of our prediction tomorrow, treating that as the actual value of tomorrow so we can make a prediction the next day, this phenomena here would, our predictions would keep getting bigger and bigger. Does everybody see that? Okay? People see what I'm trying to say. Okay, good. So what's a problem with that? It says that if we use a model like this, if we happen to be living in a world like this, and we wanted to make a prediction as to what the volatility will be a year from now, it's going to keep getting bigger and bigger. And that model doesn't work because it's a process that is sort of a mean reverting process. It tends to have a shock and then come back down. And so if you want to make long-range forecasts, you somehow have to have a model with the property that in the long run it will decay. If you make your predictions far enough out, it will decay back to the mean. And that's the kind of a reason why there are other more sophisticated models for this, like GARCH processes, which I hope we'll talk about. Any questions? Okay. Fair enough. So let's look now at any questions about volatility prediction. Okay? The way that VIX index is computed is interesting. And so if there's any questions, that's kind of an interesting thing to talk about. Any questions? Okay. Let's look now at different classes of models. When we talked about modeling, okay, we defined certain classes of models that are, let's say, common models that are interesting for predicting things. One of the simplest models, okay, that's kind of important, is things that are called the autoregressive models. Okay? A autoregressive model, okay, a leg 1 model, says that today's value, okay, of something is going to be a mean constant plus some constant times yesterday's value, okay, plus some kind of a random term, okay, an error term if you wish, okay, or a random motion. In general, when we talk about a autoregressive model with a history of P, today's value is going to depend upon P previous values. It's like a recurrence relation with history P. As computer scientists, you took a course probably in combinatorics where we talked about recurrence relations. In an autoregressive model, we say that each term is going to depend upon a history, the P previous terms. Here it depends upon the 1 previous term. Here it can depend on P previous terms. Okay? Any questions? And if we do this kind of a model, okay, what's interesting about it? If we have a model like this, what should the autocorrelation function of it look like? Okay? Let's think about this. Here we've got a that if our function depended upon the previous value, what would the let's say we have a model where today's value depends upon yesterday's value plus some other relative random terms. What do we think the autocorrelation of that function should look like for that kind of a process? what would the autocorrelation at a lag of 1 look like? Okay? We have a process with the problem that today's value depends upon yesterday's value. What should the autocorrelation look like? Okay? At a lag of 1. Big or small or 0? Should be big, right? So we would expect that there would be a high correlation, a lag. At a lag of 1, there would be a high autocorrelation, right? What about at a lag of 2? Say small? Actually, it's not clear that that's true. Okay? What is the value of r sub t? Okay? If we have a function like this, phi 0 plus phi 1 r t minus 1. What is r t minus 1 going to look like? Okay? That's going to be governed by the same kind of a process, right? R phi 1 RT minus 2. Substituting this for this, it shows that today's value is also going to depend very heavily on the value 2 periods ago. Does everybody see that? So in fact, what this process would do, even though it depends upon a history of only 1, the autocorrelation function implied by this kind of a model, okay, would be expected to decay fairly slowly. Does that make sense? So if we were given, let's say, a model like something like sales data, okay, or GDP, or something like this, one reasonable model to try to fit to it would be an auto, basically an AR model, okay, an autoregressive model. And what's interesting here is that even though there's a complicated autocorrelation function, it might be able to be captured by only one of these parameters, okay? That's the interesting thing here, okay? That the history does not need to be very large to capture complicated phenomena. Any questions? Okay? Any questions about this kind of a model? Okay? So one way that we could build a model, okay, for an arbitrary time series that I think is reasonably satisfying is to try to fit, basically, our time series to a autoregressive model of a certain history. How would we do that? Okay? Suppose I built a matrix. Okay? Let's say I wanted to build a model, let's say a model depending upon a history of p periods. Okay? Tn would be equal to what? It is going to be some constant times Tn minus 1 plus some constant times Tn minus 2 plus some constant Cp is going to depend upon Cn minus P. Does everybody see that? That's sort of somehow the nature of our model. Tn minus 1 is going to depend upon the p values before it. So that's going to be Tn minus 2, Tn minus 3, Tn minus p minus 1. Does everybody see this idea? We can build a matrix, which is sort of has this banded structure to it, okay, with the property that if we want to figure out what these constants are, the problem reduces to finding which constants times these values. We said that this is the nth term. It's going to be the dot product of these constants times this. Okay? This is the kind of a problem you can use a least squares fit to try to figure out, or a regression, to figure out what those constants are. So the good thing about one of these autoregressive models is that there is a natural way to try to find what those parameters are. Okay? So long as we have a history of points that is much larger than the number of parameters we're looking to fit, we have, if the number of parameters that we're trying to fit is equal to the number of equations, then there's only one solution. If there are far fewer parameters than the number of points, then we can now think about doing a least squares kind of a fit to find which constants will minimize the difference between the dot product of this and this. Okay? Any questions about it? So this now gives us, I think, a concrete and satisfying way to try to fit a time series function. Okay? Any questions about this? Okay? So the good news here is this gives us a way to find to build a model. How do we decide what the history should be? Okay? How many if we want to build a model like this, we could build a model depending upon a history of 1, which would just basically be this, or 2, or 3. How can we figure out how much history our model should have? Okay? What would be a way to figure that out? If I give you a time series, it should be clear that this procedure, this matrix, and solving for these coefficients will find the best coefficients to fit that. Once you've decided what the history is, how might you go about trying to select what the right history is? Any ideas? Okay? One possibility is you try first with a small, we agree that a shorter history is better than a longer history, right? So you can talk about first fitting a history of 1, and then see what the residuals look like. Okay? We would sort of think that if we have captured, okay, the history properly, if we took a look at the residuals, the differences between the predictions, okay, and the observed values, at that point, if we did the autocorrelation function, we would want it to be white noise. We would want to see no patterns in it, right? So one model of how much history to do is you keep trying, you try one history, 2, 3, 4, look at the autocorrelation function, and take the smallest value of the parameter, such that you don't see any large residuals popping up. Any questions? Okay? Does this make sense? This method should kind of make sense. Okay? And if not, we should talk about it. Any questions? Okay? Good. Now, one good thing about this kind of a model is it does provide, this kind of an autoregressive model, is it does provide a very natural way to try to capture in seasonal effects. If I built my Walmart model, okay, I could go through and say, if I tried to build it purely as an AR model, what would I do? I would try to take a look at the first history, and I'd see that today's sales depend largely upon yesterday's sales. But if I took a look at the residual autocorrelation, I would see that the residuals would still show some weekly effects and then some kind of an annual effect. If I really wanted to capture the full seasonal effect by using one of those AR models, I would have to run my model to 365 parameters if I was going to capture the year. a better way to capture sort of seasonal effects, if I know what periods matter, okay, might be to just have today's value depend upon yesterday's value, a week ago's value, and a year ago's value. And I can now solve for these coefficients in exactly the same way that I did before. Okay? Any questions about that? So the neat thing is here now, what makes this a better model? Okay? This one only has 4 parameters and captures both yesterday's values, the weekly periodicity, and the annual periodicity. Okay? Whereas if I didn't capture it in this kind of a sparse model, I would have to be solving for 365 parameters. Okay, and the results wouldn't be expected. Somehow it seems like a much more complicated model. Any questions about that? Okay. So one possibility is I identify what these seasonal periods are from my first order analysis of what's going on. Sales things should exhibit weekly and yearly periodicities. It is also possible I could have done this if I looked at the correlogram for the data and observed what periodicities did I see in it, okay, and use that to select the proper period returns. Any questions? Once I have one of these autocorregressive models, how can I use it to predict the future? Well, it was sort of like a similar model we used when we were talking about this volatility estimate. If I have a model which depends upon a certain number of previous terms, I can predict the next value just by plugging it into my equation. If I take that as being the true value, I can predict an arbitrary number of terms into the future, okay, by plugging my forecast in, okay? Any questions here? Okay? And this gives me a way to predict what's going to be going, I can predict forecast into the future as far as possible. Any questions? Okay. Any questions? There's one other. So autoregressive models are of the type that depend upon the histories of the observed values. RT depended upon RT minus 1, RT minus 2, however far your history is. There is a different class of models, which they call moving average models, which I find the term quite confusing, okay? Which will model today's value not on terms of previous values of the function, but in terms of previous values of the errors or the shocks or the random uncertainty, okay, of the function. So suppose we had a world where a process that looked something like this. The value of this function, we might say, is equal to, let's say that every day there is a certain amount of random shock, okay, a certain amount of things that happen. A random shock might be does the price go up or down, okay? We could talk about a class of models where the value of today's value depends only upon the random events, okay, that happened the previous 2 days, as opposed to the history, as opposed to the actual values of the 2 days. Okay? This is what they mean by a moving average model. Okay? And let's think about it just a little bit today, and we'll talk more about it next class. Okay? In a moving average model, let's say we lived in a world where where random events have a certain persistence, a certain amount of time that they last for. Okay? Right now we're going through there was some kind of a stock market crash. This could have happened randomly at any point. But once that thing happened, okay, there's going to be a certain impact of this random shock that's going to last for a certain time. Okay? In an MAQ model, we're going to say that random errors, when there is a random shock or a random change, that the magnitude of that difference, that event, has a persistence of Q periods before it goes away. Okay? Any questions? So let's think about what when we look at a normal random walk, okay? A random walk model said what? That today's value was going to be yesterday's value plus a random term. How much was the movement up or down today? Right? And we sort of assume somehow that these periods, these events happen, and that the random movement today has no impact on the random movement tomorrow. On the other hand, we could imagine a world where price movements today, the amount of movement today, depended somewhat upon how much movement happened 2 days ago. Okay? That would seem like, again, in the case of volatility, that's certainly true somehow. Okay? There's this longer range correlation, right? But if we could imagine that our random movements were somewhat correlated over time, then we would want to have a model where today's value depends upon the history of the random movements before that. Okay? And that's kind of what we mean to capture by an MA model. Okay? Next class we'll talk more about MA models. Okay? And how we can fold these autoregressive models and these MA models and some other factors into a very, very powerful series of time series models that captures a lot of different phenomena. Any questions? Any questions now about homework 1? It is due, I gather, at midnight. Did anybody successfully submit it? Meaning like the mechanics of the submission work. Okay? Any questions about it? If not, I look forward to seeing it, and I'll look forward to seeing you guys on Thursday. Thank you.